Magnetism is by far one of the most complicated subjects we will deal with, and is also one of the biggest subject matters we have to deal with. So we'll get through as much as we can. 5 minutes. A south pole and a north pole will attract each other, but if it was two south poles next to each other, these two would repel. So the bottom repels and the top attracts. Also, every single magnet has to have two poles. It's impossible for a magnet to have only one pole. If we took this magnet here and we broke it in half, what we would get instead is two magnets, because again, every magnet must have two poles. These magnets would be weaker than this magnet, but it would still be two magnets. Next thing you're going to have to know how to do is something called the right-hand rule. Here, we have current carrying it to the right. We need x's above or dots above and x's below or dots below. The way we do this with the right-hand rule is you're going to take your pencil and you're going to point it to the right. Your thumb wraps around. This is the way that the field's going. It's coming out of the page above. We represent out with dots. It's going into the page below. We represent in with x's. If you have a loop of wire that's carrying current clockwise, and you need to know, is it x's or dots inside? Just think of one individual wire itself. So for example, this wire here at the top, which we already know what it looks like. So for the top wire, it'll be dots above it and x's inside. That means all the others are going to follow this pattern. Dots outside, x's inside. Don't be fooled. You can never have a situation like this where you have some x's inside, some dots inside, some x's outside, some dots outside. That never happens. The other type of rule you're going to have to know is called the FBI gun law. So if we have a field going into the page, and we take a wire carrying current to the right, your palm is going to function as B. So B needs to face into the page. Your index finger is going to function as the current, so it needs to point to the right. This leaves your thumb pointing towards the top of the page, therefore the force on this wire is towards the top. The same thing will work for positive charge. For negative charge, you would use your left hand, or you could use your right hand, but it would be the opposite of what you found. So if it was a negative charge in here would go down if the charge was moving to the right. Also, in magnetism, if a charge is not moving, there can be no forces on it. Also, similarly for wires, if there's a field to the right and you have a wire in the middle of it that carries current to the right, or a wire that carries current to the left, this field exerts no force onto it because the field and the current are in the same direction. You cannot use the gun law and get your palm to face to the right as well as your index finger to face to the right without breaking the gun. Therefore, there are no forces acting on these. Remember that forces on wires is BIL sine theta. Forces on charges is QVB sine theta. Again, the top one is for wires, the bottom one is for charges. You'll also have to know about transformers. Transformers, the number of turns on the primary over the voltage on the primary equals the number of turns on the secondary over the voltage on the secondary. But one of the subtleties is the power on the primary has to equal the power on the secondary. This is by the conservation of energy. You will see this on the exam. It is designed to trick you, but the power must be the same on both sides, otherwise energy conservation has been violated. Whether the transformer is step up or step down depends on the voltage. If the voltage increased, then it's step up. If the voltage decreased, then it's step down. Another principle we'll have to talk about is flux. Flux is not fields created by the wire, but instead an external field passes through the loop of wire. It depends on three things: B, the strength of the field; A, the area of the loop; and the cosine of theta, or a fancy way of saying how this loop is positioned. In this case, the cosine of theta is 1 because theta is 0 degrees.